So, we continue our discussion on the confidence interval estimation. Let me repeat the setup here. We are interested in the comparison of the means of two normal populations. So, we have a sample x 1 x 2 x m from normal mu 1 sigma 1 square y 1 y 2 y n is another independent random sample from normal mu 2 sigma 2 square population. These two samples are taken to be independent. So, we are interested in the confidence interval for mu 1 minus mu 2, let us call it eta. So, we have earlier found out the confidence interval for the situation when sigma 1 square and sigma 2 square are known, but in general the sigma 1 square and sigma 2 square may be unknown and we may be required to find out the confidence interval. So, we take the case 2 that sigma 1 square and sigma 2 square are unknown, but equal, that is unknown, but equal variability. Now, this type of situation may arise, for example, you are looking at two brands of certain product. So, now the variability of the say average life, for example, it may be same, but average lives themselves may be different. So, in such cases this model is useful. Let us look at the analysis of this. So, as we have seen that the sampling distributions of x bar, y bar, s 1 square, s 2 square will be of interest here. So, x bar, y bar, s 1 square and s 2 square are independent. In the sampling from normal distribution we know this fact, independently distributed. Here x bar is 1 by m sigma x I is equal to 1 to m, y bar is the mean of the second sample, that is 1 by n sigma y j is equal to 1 to n. If we consider the sample variance of the first sample, that is 1 by m minus 1 sigma x I minus x bar whole square I is equal to 1 to m, and s 2 square is equal to 1 by n minus 1 sigma y j minus y bar whole square, that is the sample variance of the second sample. If we consider these quantities, then we have the following observations, that is x bar follows normal distribution with mean mu 1 and variance sigma square by m. So, here sigma 1 square and sigma 2 square both are same. Then y bar follows normal mu 2 sigma square by n. So, if we consider here x bar minus y bar, that will follow normal with mean mu 1 minus mu 2 and variance will be sigma square 1 by m plus 1 by n. So, if we want, so this is the quantity eta. So, we get x bar minus y bar minus eta divided by sigma and root of this, that is root of m n by m plus n, that will follow a standard normal distribution. However, this involves the unknown parameter sigma also. So, we cannot straight away use it as a pivot quantity. So, we need a estimator for sigma also. So, we can get it here by considering m minus 1 s 1 square by sigma square follows chi square on m minus 1 degrees of freedom, and n minus 1 s 2 square by sigma square follows chi square on n minus 1 degrees of freedom. Once again these two quantities are also independent. So, I can add these and we get m minus 1 s 1 square plus n minus 1 s 2 square divided by sigma square, that follows chi square distribution on m plus n minus 2 degrees of freedom. Let me define a quantity S p square, that is equal to m minus 1 S 1 square plus n minus 1 S 2 square divided by m plus n minus 2, that is pooled sample variance. If we use this pooled sample variance, then what we are having is m plus n minus 2 S p square by sigma square is following chi square distribution on m plus n minus 2 degrees of freedom. Now, we have the distribution of x bar minus y bar minus eta divided by sigma multiplied by a constant as a standard normal distribution, and let me call this quantity as say z, and I have a quantity, let us call it say w. This is having a chi square distribution. Another thing we can notice here is that z is involving only x bar and y bar, and w is involving only S 1 square and S 2 square, that is S p square. So, z and w are independently distributed. So, if they are independently distributed, I can look at the distribution of z divided by w by m plus n minus 2 square root, that will have t distribution on m plus n minus 2 degrees of freedom. So, this quantity is equivalent to root m n by m plus n x bar minus y bar minus eta divided by S p. So, that follows t distribution on m plus n minus 2 degrees of freedom. Now, let us observe, given the samples x i's and y j's, we can evaluate x bar, y bar and S p, and this involves the parameter eta for which we need the confidence interval, and the distribution of this quantity is free from the parameters of the distribution. Therefore, this value t can be considered as a pivot quantity, and we can make use of this to construct a confidence interval for eta, that is mu 1 minus mu 2. So, we look at the t distribution, it is symmetric about the axis, it is symmetric about 0, and so this is f m plus n minus 2 t. So, we look at the point here, this point is t alpha by 2 m plus n minus 2, and we have on the left hand side the similar point, that is minus t alpha by 2 m plus n minus 2. So, this intermediate probability is 1 minus alpha, and we are in a position to write the statement that probability of minus t alpha by 2 m plus n minus 2 less than or equal to t is less than or equal to t alpha by 2 m plus n minus 2, that is equal to 1 minus alpha. So, expanding this t and then adjusting the terms, we will be able to construct a confidence interval for mu 1 minus mu 2. So, t is here square root of m n by m plus n x bar minus y bar minus eta divided by S p, that is less than or equal to t alpha by 2 m plus n minus 2, that is equal to 1 minus alpha. So, this is equivalent to root m plus n by m n S p t alpha by 2 m plus n minus 2 less than or equal to x bar minus y bar minus eta less than or equal to square root m plus n by m n S p t alpha by 2 m plus n minus 2, that is equal to 1 minus alpha. So, this means that x bar minus y bar minus root m plus n by m n S p t alpha by 2 m plus n minus 2 less than or equal to x bar less than or equal to eta less than or equal to x bar minus y bar plus that is equal to 1 minus alpha. So, in the situation when the variances of the two populations are unknown, but equal, the confidence interval for mu 1 minus mu 2 is obtained as x bar minus y bar plus minus square root m plus n by m n s p t alpha by 2 m plus n minus 2. So, this is giving a 101 minus alpha % confidence interval for mu 1 minus mu 2. Notice here is that since the variances were assumed to be equal, we are making use of a pooled sample variance. Now, one may ask a question that in place of this, suppose we consider simply S 1 square or S 2 square only, because in that case also we are getting a variable which is free from the, which is having a distribution free from the parameter. So, why not use only this or only this? The question is that if we use only say S 1 square, then the degrees of freedom that we will get for the t variable will be m minus 1. So, if we get only m minus 1, then in that case the interval will be having the width x bar minus y bar plus minus square root m plus n by m n. Now, this term will not come here, rather we will have S 1 only, this coefficient will not come here. Here we will have only S 1 and the degrees of freedom will be m minus 1. Naturally, the length of the interval will increase if we have less degrees of freedom. So, in order to get more accuracy or you can say more precision, we need a smaller interval with the same confidence coefficient. Therefore, it is beneficial to use more information here. Let us take the case when both mu 1 and mu 2 may be unknown. Then let us look at the procedure here that has helped us to create this confidence interval. The procedure that we adopted was that the distribution of S p square by sigma square, that is chi square, and the z variable that we utilized, that also has a sigma in the denominator. So, we were able to get rid of this. If the variances are not equal, then in the first place we will be getting sigma 1 square here and here we will get sigma 2 square. So, when we add the two terms in the denominators, I will get S 1 square by sigma 1 square and here S 2 square by sigma 2 square, and the same thing will happen with the z also, where we will get sigma 1 square by m plus sigma 2 square by n. So, in no way by taking the ratios I can get rid of sigma 1 square and sigma 2 square. Actually, it turns out that there is no exact confidence interval, that means the interval which is having the length a shortest length and as well as a fixed confidence coefficient, that means the distribution free term we are not getting. In this case, this is known as a Variance Fisher situation. So, we will consider this case sigma 1 square is not equal to sigma 2 square and unknown, that means they are completely unknown. In this case, a approximate confidence interval is proposed based on, let us call it T star, that is x bar minus y bar minus eta divided by square root S 1 square by m plus S 2 square by n. So, how this has come? In the first case where sigma 1 square by m plus sigma 2 square by n was there, we have simply replaced sigma 1 square and sigma 2 square by their unbiased estimates. So, it was proved by Welch etcetera that this is having has approximate, this has approximately t distribution on new degrees of freedom, where nu is given by S 1 square by m plus S 2 square by n whole square divided by S 1 square by m square into m minus 1 plus S 2 square by n square into n minus 1. It is by Welch and it is known as Smith-Sartor-Waite formula. So, now this need not be an integer. So, nu is rounded off to the nearest integer or integral part. That means, suppose it is turning out to be 11.37, we take only 11. So, using this one can write a confidence interval using T star, we can construct a 100 1 minus alpha percent confidence interval for mu 1 minus mu 2 as x bar minus y bar plus minus t alpha by 2 nu square root of S 1 square by m plus S 2 square by n. This will be the confidence interval when there is no information about the equality of sigma 1 square and sigma 2 square. Now, there is another situation which occurs quite frequently. For example, we are considering the comparison of the two training procedures. So, suppose there are two training procedures for certain learning. So, we select say 10 pupils and we give them instructions using one training procedure. A test is conducted to measure the outcome of that. Now, for the same set of 10 pupils, another learning procedure is imparted for a fixed period of time and another test is conducted. Now, the scores are not independent because our subjects are not independent, same people, same set of people has been selected. For example, it could be some weight reduction procedure, like the fatty people are there and we are giving them certain weight reduction program. So, by taking certain procedure for 1 month, their weight is reducing by this much. Now, for the same set of people, another procedure is adopted, then how much weights have been reduced. So, we compare the same set of people with respect to their scores. So, here this is related to paired observations. Paired observations. So, here although you are saying x 1, x 2, x n say follow normal mu 1 sigma 1 square and y 1 y 2 y n, they follow normal mu 2 sigma 2 square, but actually the sample has not been selected in this way because these observations may be paired. So, basically the model becomes that x 1 y 1 x 2 y 2 x n y n, this is having some sort of bivariate normal distribution with parameters mu 1 mu 2 sigma 1 square sigma 2 square and some correlation coefficient rho may be there. Once again we are interested in the interval for mu 1 minus mu 2, that is we want to look at the difference in the average effectiveness etcetera. A simple procedure for this is obtained by using the linearity property of bivariate normal distribution, because we know that if the random variable x y is having a bivariate normal distribution, then any linear combination a x plus b y is again having a univariate normal distribution. So, here if I make use of say observations, let me call it d I, that is equal to x I minus y I, then that will follow normal distribution with mean mu 1 minus mu 2 and some variance, let me call it sigma d square. Actually, it will be sigma 1 square plus sigma 2 square minus twice rho sigma 1 sigma 2. So, sigma 1 square plus sigma 2 square minus twice rho sigma 1 sigma 2. Let me call it sigma d square. That is not important here, because they are all unknown and we need only an estimate of this, because we are interested here in the confidence interval about mu 1 minus mu 2. So, we can make use of, now this looks like a problem of the confidence interval for a mean of a normal distribution, which we have done in the first place. So, we can consider say d bar as 1 by n sigma d I is equal to 1 to n, and we consider s d square as 1 by n minus 1 sigma d I minus d bar whole square. So, if we look at this, then we can see that d bar follows normal eta sigma d square by n, and so from here we can get d bar minus eta root n by sigma d follows normal 0 1. Also n minus 1 s d square by sigma d square, that will follow chi square distribution on n minus 1 degrees of freedom, and once again these two variables will be statistically independent. So, using this we can write square root n d bar minus eta divided by s d, that will be having a t distribution on n minus 1 degrees of freedom. Now, observe this function here, it is involving the random variables, that is the observations x I and y i's, d bars are the mean calculated from the differences, and s d square is calculated as the variance of the difference observations, and here the parameter of interest eta is appearing and sigma I squares etcetera are absent here. So, this can be used as a pivot quantity, and we create a confidence interval by writing down from the distribution of the t on n minus 1 degrees of freedom. So, this probability is 1 minus alpha, and we get x d bar minus s d by root n t alpha by 2 n minus 1 to d bar plus s d by root n t alpha by 2 n minus 1. So, this becomes 100 1 minus alpha percent confidence interval for eta, that is equal to mu 1 minus mu 2. So, we observe here that all these cases are differently handled, that is when we observe a sample we have to look at carefully. So, if the variance is known to us, then we have some procedure. If the variances are unknown, but we suspect that the variances may be equal, then we have another procedure. If the variances are completely unknown, then we have another procedure. On the other hand, if the sampling is not done in the independent fashion, that means we have a correlated observations, then we may arrange the data in a paired way, and then we can apply a pairing formula. So, the confidence interval for the same parameter mu 1 minus mu 2, when we are sampling from two normal populations, it is dependent upon the situation. We have to, a statistician has to carefully see that which type of method will be adopted here for finding out the confidence interval, otherwise he will be coming up with the faulty conclusions. Let me take up some examples here to illustrate these situations. So, to compare to compare the strength, the gripping strengths of left hand and right hand of 10 left-handed persons. The measurements are made on 10 persons and the data is observed. So, left hand and right hand. And we have persons 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. The gripping strengths are measured as 140, 90, 125, 130, 95, 121, 85, 97, 131, 110. For the right hand it is 138, 87, 110, 132, 96, 120, 86, 90, 129, 100. So, we need the confidence interval for say mu 1 minus mu 2. Now, observe here that this is the data related with the correlated observations. So, we will need here the means of, so let me call this as the first set. So, this is x I data, this is y I data. So, we will look at d i's, the differences here. So, the differences here is 2, 3, 15, minus 2, minus 1, 1, minus 1, 7, 2 and 10. So, we look at the d bar value here, which is the mean of this, that is 20. So, 17, 24, 26, 36. So, that is 3.6. Similarly, we calculate S d, that will be equal to 1 by 9 sigma d I square minus d bar square. So, once again it can be easily evaluated, it is 4 plus 9 plus 225 plus 4 plus 1 plus 1 plus 1 plus 49 plus 4 plus 100 minus 3.6 square. So, this value can be evaluated. Now, we look at the value of t on, suppose we want a 90% confidence interval. So, we need 0.059, that is equal to 1.833. So, we get the confidence interval as 3.6 plus minus S d by root 10 into 1.833. That will be the confidence interval for the difference in the gripping strengths of the left hand and the right hand of the left handed persons. Let me take another example here. To compare age at marriage of women in two ethnic groups. A random sample of 100 women is taken. And we observe that x bar is equal to 18.5 years, y bar is equal to 20.7 years, and S1 is equal to 5.8, S2 is equal to 6.3, and we want say a confidence interval for this. So, we calculate here that we may use the model for SP square. So, SP square is equal to m minus 1 S1 square plus n minus 1 S2 square divided by m plus n minus 2, that is equal to 99 S1 square plus 99 S2 square by 198, that is equal to 5.8 square plus 6.3 square by 2. So, this value can be evaluated. In a similar way, so we have the confidence interval as x bar minus y bar minus root m plus n by m n, that is, and then S p into t alpha by 2. Suppose I want 90% confidence interval. So, 0.05, and the degrees of freedom will be m plus n minus 2. So, this value we can see t 0.05198, which is almost as the normal distribution 1645. So, we substitute these values here, 18.5 minus 20.7 minus this is 100 plus 100, that is 200 by 100. So, that is root 2 by 10 into 1.645. So, plus minus, that gives the confidence interval for the difference in the ages at marriage of women in two ethnic groups. So, here we have used the pooled formula. We may actually do a testing of hypothesis for sigma 1 square is equal to sigma 2 square, and if sigma 1 square is equal to sigma 2 square is accepted, then we may go for this formula. Let me take another example here. Two machines are used to fill plastic bottles with dishwashing detergent. The standard deviations of fill volume are known to be sigma 1 is equal to 0.15 fluid ounces and sigma 2 is equal to 0.12 fluid ounces for the two machines. Now, two random samples of N 1 is equal to 12 bottles from machine 1 and N 2 is equal to 10 bottles from machine 2 are selected, and the observations are x 1 bar is equal to 30.87, x 2 bar is equal to 30.68. So, find 95% confidence interval for mu 1 minus mu 2. So, here we can see we can look at the confidence interval as x bar minus y bar plus minus square root sigma 1 square by m plus sigma 2 square by n z 0.05. Now, z 0.05 we can see from the tables of normal distribution, it is 1.645. So, this interval becomes 30.87 minus 30.68 plus minus square root. Now, sigma 1 square is 0.15 square by 12 plus sigma 2 square is 0.12 square by n is 10 multiplied by 1.645. So, after simplification these values turn out to be 0.095 to 0.285. So, this is 90% confidence interval for the mean difference, that is mu 1 minus mu 2. So, here the variances were known, sigma 1 square and sigma 2 square. So, we have adopted a procedure where the formula for known variances is utilized here. Let me take another example here. The capacities of batteries. So, these are measured in say ampere hours. They are distributed as normal mu sigma square. The records for 10 batteries are say 140, 136, 150, 144, 148, 152, 138, 141, 143, 151. We want 99% confidence interval for sigma square. So, now here we will make use of the fact that mu is unknown. So, if mu is unknown, then the formula for confidence interval for sigma square is based on chi square on n minus 1 degrees of freedom. The formula is n minus 1 s square by chi square. So, 0.005 n is 10. So, this is 9 to n minus 1 s square by chi square 0.0959. So, 995. So, these values we see from the tables of the chi square distribution, that is chi square 0.0059, it is 23.59 and chi square 0.995 on 9 degrees of freedom is 1.73. So, s square we calculate here, it is turning out to be 32.23. So, after substitution of these values, the confidence interval turns out to be 12.30 to 167.21, which is pretty large confidence interval, but that will be there because we are considering for sigma square and the variability of the original sample itself is large. This is s square is 32.23 here. If we reduce the confidence level, suppose we make it 90%, then this will be shrinking. Since we have made a very high confidence level, that is why the confidence interval is very large, which looks slightly impractical also. Next, we look at the confidence intervals for variances. So, comparing variances. Again we have two cases, that is mu 1 and mu 2 are known. If mu 1 and mu 2 are known, then we make use of sigma xi minus mu 1 square by sigma 1 square following chi-square distribution on m degrees of freedom, and sigma yj minus mu 2 square by sigma 2 square follows chi-square distribution on n degrees of freedom. So, if we take the ratios here, sigma xi minus mu 1 square by sigma 1 square pi m. So, that is m here divided by sigma yj minus mu 2 square by sigma 2 square. So, that will come in the numerator divided by n, that will have chi square f distribution on m and n degrees of freedom. So, if we look at this quantity, if mu 1 and mu 2 are known, then here the ratio sigma 2 square by sigma 1 square is coming. Let us denote it by say psi, that is sigma 2 square by sigma 1 square. So, we are having, and let me use the notation say u as m sigma xi minus mu 1 square divided by n sigma yj minus mu 2 square. So, if we look at this one, then we are having u psi following f distribution on m n degrees of freedom. So, if we make use of the tables of f distribution, that is f on m and n degrees of freedom here, and f 1 minus alpha by 2 on m n degrees of freedom, this is alpha by 2 and this is 1 minus alpha by 2. So, this is 1 minus alpha. So, probability of f 1 minus alpha by 2 m n less than or equal to u psi less than or equal to f alpha by 2 m n, that is equal to 1 minus alpha. So, we can write probability of u. So, divided by f of alpha by 2 m n less than or equal to sigma 1 square, that is 1 by psi, it becomes sigma 1 square by sigma 2 square less than or equal to u divided by f 1 minus alpha by 2 m n, that is equal to 1 minus alpha. So, we have a 1 minus alpha confidence interval for sigma 1 square by sigma 2 square. This can also be written as u f 1 minus alpha by 2 n m to u f alpha by 2 n m by using the ratio, or you can say reciprocal property of the f distribution, because we know that 1 by f m n is 1 by is equal to f n m. So, this property can be utilized here. Let me give one example here for confidence interval for the ratios. So, two brands of say cuff medicine are given and the response times are measured in days. Okay. So, here we are having the data m is equal to say 10, n is equal to 12, S1 and we are getting the observations as x1 is equal to say 2, 3, 2, 4, 2, 5, 6. So, 3, 7 and then 1, 2. So, we have 10 data here and for y we have the data say 3, 4, 6, 8, 3, 2, 9, 5, 11, 7, 2, 1. Now, based on this we calculate x bar, y bar and we calculate sigma x I minus mu 1. So, it is given that mu 1 is say 3 and mu 2 is equal to 5. So, if we are looking at sigma x I minus mu 1 square and sigma y j minus mu 2 square, then that will follow chi square on 9 and this divided by sigma 2 square will follow chi square on 11 degrees of freedom. So, we can construct 10 sigma x I minus mu 1 square by 12 sigma y j minus mu 2 square and then we need to look at the tables of f on say 0.05, 10 and 12 degrees of freedom. Now, another situation may occur when mu 1 and mu 2 are unknown. If mu 1 and mu 2 are unknown, then we will not be able to make use of the formula that we derived earlier, because there in the confidence interval mu 1 and mu 2 are actually appearing. So, what we do, we make use of S 1 square and S 2 square. So, we have m minus 1 S 1 square follows chi square distribution on m minus 1 degrees of freedom and n minus 1 S 2 square by sigma 2 square follows chi square distribution on n minus 1 degrees of freedom. Furthermore, these two random variables are independent. So, we can make use of the ratios m minus 1 S 1 square by sigma 1 square divided by m minus 1 divided by n minus 1 S 2 square by sigma 2 square into n minus 1, that will follow f distribution on m minus 1 n minus 1 degrees of freedom, which is reducing to sigma 2 square by sigma 1 square S 1 square by S 2 square. This follows f distribution on m minus 1 n minus 1 degrees of freedom. So, making the use of distribution of f, that is we have f alpha by 2 m minus 1 n minus 1 and f 1 minus alpha by 2 m minus 1 n minus 1, intermediate probability is 1 minus alpha. So, probability that f 1 minus alpha by 2 m minus 1 n minus 1 is less than or equal to sigma 2 square by sigma 1 square S 1 square by S 2 square is less than or equal to f alpha by 2 m minus 1 n minus 1, that is equal to 1 minus alpha. So, we make use of this and adjust the coefficients as probability that S 2 square by S 1 square f 1 minus alpha by 2 m minus 1 n minus 1 less than or equal to sigma 2 square by sigma 1 square less than or equal to S 2 square by S 1 square f alpha by 2 m minus 1 n minus 1, that is equal to 1 minus alpha. So, we are getting 101 minus alpha % confidence interval for sigma 2 square by sigma 1 square. We can reverse it if we want for sigma 1 square by sigma 2 square, then we interchange the roles here, we put sigma s 1 square by s 2 square and the degrees of freedom will get reversed, it will become n minus 1 m minus 1. So, we give one example here. So, s 2 square by s 1 square f 1 minus alpha by 2 m minus 1 n minus 1 2 s 2 square by s 1 square f alpha by 2 m minus 1 n minus 1 is 100 1 minus alpha % confidence interval for sigma 2 square by sigma 1 square. So, say viscosity of 2 brands of oil used in car is measured and the following data is recorded. So, from brand 1 you have 10.62, 10.58, 10.33, 10.72, 10.44. For brand 2 it is 10.50, 10.52, 10.62, 10.53. Suppose we want a confidence interval for sigma 2 square by sigma 1 square. So, we will calculate the values here s 1 square, s 2 square. So, s 1 square turns out to be 0.02362, s 2 square is equal to 0.002825. You can see here there is a 10 times difference here. So, the f value that s 2 square by or you can say s 1 square by s 2 square will be equal to 8.36. So, if we look at the f value on 0.05, say 1, 2, 3, 4, 5. So, 3 degrees of freedom, that is equal to 9.1172 and f value 0.9543, that is equal to 0.1517. So, a 90% confidence interval for sigma 1 square by sigma 2 square, that will be equal to 8.36 into 0.1517 to 8.36 into 9.1172. So, this is the confidence interval for the ratio of the variances here. So, in a given practical situation, we need to analyze that what is the model that will be applicable and accordingly we make use of the formulae. So, for example, when we are looking at the confidence intervals for mu 1 minus mu 2, then we worry about that what is the status of the variances. If the variances are known, then we have some formula. If that is based on the z, that is normal distribution. If we have variances unknown but equal, then we have a formula which is based on a t distribution based on the pooling of the concept, pooling of the variances. And if we have variances to be completely unknown, then in that case we have another approximate t distribution formula and we make use of that. On the other hand, if the data is correlated, then we make use of pairing and a pair t formula is used. Similarly, when we are worried about the confidence interval for the sigma 1 square and sigma 2 square, then we look at the knowledge about the means. If the means are known, then we have a formula based on f distribution on the total degrees of freedom m and n. If the means are unknown, then we have another formula which is based on s 1 square, s 2 square, and the degrees of freedom are slightly reduced to m minus 1, n minus 1. Now, these formulae are quite standard because they are making use of the sampling distributions from the normal populations. When we do not have normal populations, then in that case we may have to look for appropriate sampling distribution. For example, if we are dealing with uniform distribution, if we are dealing with from the exponential populations, then we look at from the description that what is the sufficient statistics. From there we find out the pivoting quantity if we are able to derive the sampling distribution of that. So, the techniques for that and also for the proportions are available, and one can work out various formulae for confidence interval from other populations as well. So, that is part of another course, that is statistical inference, that we will be doing later on.